century trying to get from one place to another. We'd just be using steam engines or internal combustion engines rather than horses. What gave us an automobile culture and kind of revolutionized the world was the pneumatic tire, that you could put a tire on an automobile and you could drive it down the road without tearing up the road. Once that happened, once the tire was invented, the automobile exploded. And they didn't entirely replace railroads. There's still good reason to have railroads, but for ordinary transportation, we went to cars. And rubber was why. Now, where does rubber come from? Okay. Remember, in natural rubber, we have this cis configuration, which gives us a very, very kink molecule. I haven't drawn a kink here. You can see it kind of has to be, because the CH3 is big and the H is also on this side. So I'm going to get a very kink molecule. It's going to be rather difficult to keep for these things to, well, it's fairly easy for them to fly over one another because of the very regular shape. What happened by accident in Goodyear's case was you heat this up with sulfur. If you heat it up with sulfur, which is S2, then you can get a reaction in which the sulfur bond breaks and it bridges itself to the two bare carbons on adjacent chains, basically replacing these two double bonds with bonds to sulfur. That provides a cross-link between the two chains, and it's one example of the many, many different kinds of cross-link polymers that we have today, which are basically a way of combining the properties of a linear chain with a polymer with those of a network polymer. Because we can take the chains and using chemical reactions, tack them together at various points, and create a semi-three-dimensional network. Yeah?
So, in racing cars, we got soft rubber. Is that just less sulfur in the compound?
The chemistry of tires is a very serious field in itself. It's very complicated. Let me finish this and I'll tell you a little bit about tires. Okay. So what do we do? This is the first of many, many elastomers, which are made of network polymers. If you imagine the shape of natural rubber, it looks kind of like a spring because of the severe kinking where you have the double bond. So I have a bunch of springs sitting here right next to each other. If I pull on them, they will stretch. The problem is they won't snap back into their original configuration because they'll just slide. But if I cross-link them periodically, then I make a network. I make a framework. And that framework will have a definite relaxed configuration because these cross-links will want to configure themselves geometrically in some definite low-energy pattern. So if I take something that looks like this, you might imagine a few more cross-links back here, and pull that, then it will stretch like a spring, but when I let it go, these cross-links will restore it to its initial configuration. So I now have a functional elastomer. Very large elastic elongation, but it snaps back into its original configuration when I let it go, and I can build three-dimensional objects out of that like tires. Well, obviously, if I'm going to do this, I can control the rigidity of this piece by controlling the number of crosslinks. The more crosslinks I have, the more rigid it is. The harder it's going to be to stretch, but also the more firmly and vigorously it will snap back into its previous configuration. So from that point of view, you say, wow, I want a good hard tire, let me put in lots of crosslinks. However, if you can make the material too rigid, it can actually become somewhat brittle if the number of crosslinks gets too high. If you make it into actually a three-dimensional polymer, you lose your elasticity. So there's an optimal crosslink density that you want in something that you would use for a particular application. But if you want a tire, it's not just the rubber and the elastomer. You have all kinds of other things in a tire. You have fillers that are intended to give color, that make it wear in a certain way. You know, your tires, what you worry about with your tires is how quickly do they wear. The wear of just natural rubber, even vulcanized rubber, the wear rate is very high. A tire just made out of normal vulcanized rubber wouldn't last very long at all on our roads because it just drives away against them. So you have to add things to the rubber, which are fillers. They may be, imagine hard particles, that's one kind of filler. So that you have this rubber and just spread densely throughout the rubber all these hard particles. When the tire hits the road, it's the hard particles that are taking the wear, and as a consequence, the wear rate goes way down. That's oversimplifying the problem, but that's something we have to worry about. There are many other things we have to worry about in making tires. One of the most interesting of them is the disposal problem, or the recycling problem, if you want. Very much recycling a tire. What do you do with the tire when you're finished with it? What do we do with tires when you're finished with it? This is a thermosetting polymer, basically. You heat it up, you can burn it. In fact, I don't know if you've ever been around a place where a pile of tires caught on fire, but it produces a huge smoke, a terrible smell, it destroys the neighborhood for weeks. And it's happened there. So what do you do with these things when they're finished? And there have been all sorts of proposals because we go through an enormous number of tires in the United States. We have an incredible number of tires every year that need to be disposed of. So how do we dispose of them? Well, there have been various ideas. One of the best ones recently is you take the tires, you freeze them in liquid nitrogen, so they become brittle for reasons we'll talk about later. You then crush them into very small pieces while they're brittle, and you use that for using asphalt and things of that sort. So they're getting rid of these things is something wrong. But anyway, basically this is what elastomers are all about. Not just tire rubber, but all elastomers. They are long chain polymers that are kinked so that they look and act like little springs. They are cross-linked by sulfur or by some other chemical reaction so that the springs are joined together and form a three-dimensional configuration that is reproducible, that will recover itself, that will restore itself when it's spread and let go. And that's where the elastomeric industry came to be. Silicates, rocks and minerals. I don't think I'll get to fibers today. This is what's called an EDEX, Energy Dispersive X-ray Analysis trace of Tilden Park dirt. Believe it or not, I was once involved in failure analysis in which it was critical to know what the spectrum of ordinary dirt looked like. And this is the spectrum of Tilden Park dirt. Virtually any dirt taken anywhere in the world will give you almost the same spectrum. If I were to take the dirt from campus instead of up there, it would look a little bit different. Anyway, the height of these peaks, it's not exactly true, but to a first approximation, the height of these peaks is telling you the composition of the various elements that are present. So what you can see is that Tilden Park dirt, like almost all dirt, is basically aluminosilicate. High in aluminum, high in silicon, high in oxygen. In fact, it's much higher in oxygen than this peak would lead you to believe. And it's what we call an aluminosilicate. It's kind of like SiO2. There are, of course, lots of other minerals that are stuck in the dirt, in this case iron, titanium, calcium, sodium, potassium, some magnesium, a little bit of carbon, and some organic stuff in the dirt. If I took that same sample down here on campus instead of up on the hill, the first thing I'd notice is a chlorine peak. Because down here we're getting a fair amount of sea air from the bay, and so if you take the dirt outside, you'll see chlorine. You get up top of the hill, you see very little chlorine. This is what the world is made out of. And it was the first material that primitive engineers, if you want, had the opportunity to work with. And what they did with this material, or variants of it, was to create the Stone Age. Now, part of the Stone Age was stone, what people could do with stones, like make arrowheads and so on. But the real engineering part of the Stone Age was when they could make pottery and other things, statues, where you could shape the dirt and then turn it into a permanent object, when essentially you could create stone in the form in which you wanted the stone. So let's talk just a little bit about pottery and how you make stone. Well, let's go first. I already told you about this, really. Let's forget about the aluminum and pretend that dirt is nothing but SiO2, because the basic principles are what the SiO2 is doing. As I told you last time, SiO2 is based on the SiO4 tetrahedron. And you can imagine the SiO4 tetrahedron configuration by inscribing it inside a cube, in which case you'll have a silicon atom here in the center, and you'll have oxygen atoms at 4 of the 8 corners, forming a tetrahedron. Now, I can make a three-dimensional structure out of that by joining these things together at the corner. You see it here. This oxygen is joined to that silicon and this silicon, which means that this cube is joined to that cube at its corner, and so on. If you fill out all of the corners, you have SiO2 stoichiometrically. Now, as I described, and maybe this picture shows a little better than what I showed you last time, because this is a very open structure, and because I can rotate the cubes around their joint bond and do various other things to reconfigure them, there are in fact quite a few different organized three-dimensional structures that I can make by joining these little cubes at corners. And if you look just at quartz, there are several different crystal structures that are found in quartz, and that's the reason why. It's also fairly easy to form glasses from that to make it disordered. Even easier if I add in some ions like this, which seal off those oxygen bonds and prevent the corners of these cubes from being shared with one another. We talked about glass formers last time. This is essentially how a glass former works. Well, the three-dimensional structures of silica give us the ordinary rocks you find in nature, a lot of the minerals that you find in nature, and the glasses that you find in nature that you can create yourself. However, it is also possible, and this is not nearly as good a drawing, but suppose I take these blocks and I join 3 of their corners but leave the other dangling. I can join those 3 in a plane, so I get a structure that looks like this. It has a dangling bond here on the top. All these little pyramids are pointed up, tetrahedra pointed up, and I have created a sheet of SiO4 tetrahedra. That is the structure, or is half of the structure, that forms naturally as clay in the earth. The clays are minerals in which 2 of these sheets get together like the lobes of a sandwich, and ions, or layer of ions, get here in the middle to bond them together. You have mica, for example, which you may be familiar with, which comes out of these very, very tiny, thin little sheets. Those are basically just 2 silicate layers bonded by ions. All of the world's clays are essentially the same thing. Now, the very nice thing about these clays is that they are easily molded and deformed. Because suppose I take the clay, and a good clay is really looked at microscopically, just tiny little flakes, and I add water. The water will tend to get tied up in between the flakes, and I now just kind of mold it with my hand. Well, I can deform it into pretty much any shape I want to rather easily, because what I'm doing is moving these flakes, and they're lubricated by the water that are in between these 2 layers. So I can take clay and mold it into shape. You see, that's great. If I'm an ancient potterer, I take my clay, I mold it into a bowl, put it out in the sun to dry, and I have a bowl. Because as soon as I put it out in the sun to dry, the water comes out, this thing crumbles back into clay again. So I've accomplished nothing. But what I can do is I can take that clay, once I have molded it into the shape I want, and I can fire it. If I fire it at high enough temperature, I will first drive out the water. And then, at high enough temperature, these bonds become sufficiently agitated that they recognize that they don't want to be 2-dimensional structures. They would prefer to be 3-dimensional structures. They're geological processes that cause these clays to form. They want to be 3-dimensional structures, so these bonds will break and reorganize themselves and wind up looking like that. And that's essentially what's going on in pottery. You are taking clay, which is an unstable form of silicate. You're using the 2-dimensional flake properties of that clay, mixing it with water, forming it into whatever shape you want it to be, a plate, a bowl, a statue, whatever you're looking for. And then having done that, you then fire it at high temperature, which gave rise to the first really efficient furnaces in the history of the world, that allows it to reconstitute itself from clay to stone by reorganizing the 2-dimensional bonds into these 3-dimensional bonds. And that's basically what pottery is all about, as we still do it today. Pottery was an enormous breakthrough in the technological history of the world, enormously important, because not only did it give people the chance to actually make objects by forming them and then firing them, but as soon as people learned how to make clay pots, almost immediately they said, well, these clay pots are kind of ugly, let's decorate them. So they started looking in the earth for things that could, glazes, things that you could put on the surface of the pots. They would give them colors, that you could paint figures and all sorts of things. And so chemistry was born, because people started looking for things in nature that by heating them up, they could get them to change color or change glaze or do various things. And immediately over several thousand years actually, but steadily, people became more and more adept and knowledgeable in producing glazes and beautiful patterns on pots. And in the course of that, they became more and more adept at controlling the minerals around them and using those minerals for engineering purposes. Among other things that they discovered in the course of doing that was that certain of these minerals, particularly things that were rich in copper, if you heat them up just right, you would get these tiny little shiny flakes that would appear in the glazes. And we don't know the exact sequence, but at some point someone said, well, these tiny little flakes are kind of interesting. Maybe I can make bigger little flakes. And before too long, they hit a ball of copper. And once they hit a ball of copper, then they started metallurgy. And so that the belief is, and I think it's correct, that the invention, discovery of metals and how to make metals came out of the use of copper in glazes on pottery, which caused people to get more and more elaborate in what they were doing and gradually to come up with metals. Interestingly, in almost all of these things, if you go back in history, you see materials introduced. The first application of almost any new material, this would be good ceramics, copper, bronze, iron, almost anything, aluminum, jewelry. The first place it appears in 1 of 2 uses, either as jewelry, ornamentation, or as religious objects. You find tiny little religious statues, you find ornamentation that people wore. The reason, of course, is that when you first get hold of the material, because it's a real challenge to make it in the beginning, it's enormously expensive. So you take it, you use it for objects that are inherently expensive, ornamentation, religious artifacts. And then later, as you learn to handle it, then more and more and more uses come into being. It may be funny to you that I included aluminum. Aluminum, which is one of the most common species on the earth, you just saw that aluminum dirt, is also one of the most difficult to extract because it makes very stable oxides. So there was, in the court of Louis XIV in France, when he had a fancy state dinner, the super honored guests were permitted to eat with aluminum forks. The lesser nobility had to make do with gold and silver. Well, somebody in the 19th century figured out how to extract aluminum, and the rest is history. But for a very long time, it was a very, very rare and very expensive metal. I think that's, well, I'm better. Yeah, let's quit there. We'll do fibers and biological molecules next time.